All right, this is part 2 of chapter 5. Section 2 is where we're jumping straight to the natural logarithmic function integration. So the logarithm integration, if u is a differentiable function of x, then the antiderivative of 1 over x dx is the natural log of the absolute value of x plus c. Same thing with our u, the antiderivative of 1 over u du is equal to the natural log of absolute value of u plus c. So, the antiderivative of 2 over x dx. Remember, we can take that 2 out front and do the antiderivative of 1 over x dx. Now, the reason we can't use the power rule, let's just take a little side note over here. If I did just the basic power rule, right, I would rewrite this as x to the negative first power dx. Well, I would add 1 to my power, making it 0, and divide by the new power, which is 0. Can't do that. So, it's important to remember this rule. 2 times the natural log of the absolute value of x plus c. There's our answer. 1 over 4x minus 1 dx. This one requires us to go straight to u substitution. So our u is the denominator, 4x minus 1, which means du is 4 dx. Well, I don't see a 4 in the function, so I'll divide that 4 over. 1/4 du is equal to dx. So that means I rewrite my integral as 1 over u times 1/4 du. We can bring that 1/4 out front. 1/4 times the antiderivative of 1 over u du. Well, the antiderivative of 1 over u is natural log of the absolute value of u plus c. Now we just plug back in our u. 1/4 times the natural log of the absolute value of 4x minus 1 plus c. Now why the absolute value? Remember that you can't take a natural log of a negative number. So if this derivative existed, this had to have been a positive number. Therefore, we know it's an absolute value. Let's find the area of the region bounded by the graph of this function, the x-axis, and the line x equals 3. So we want to figure out actually where it crosses the x-axis to know where we start. So where is this function equal to 0? Well, that's a pretty straightforward one when x is 0. So we're going to find the antiderivative from 0 to 3 of x over x squared plus 1 dx. That's what this is a fancy way of saying. Well, to do that, we need to use u substitution. Set u equal to my denominator, which means du is 2x dx. Notice that this here is u. So that means we want the rest to be du. I just have an x, so I need to get that 2 out of there. 1/2 du equals x dx. So now we'll replace the x dx with 1/2 du. We'll replace the x squared plus 1 with an x, or a u. So we have the antiderivative of 1 over u times 1/2 du. Now for a definite integral, remember that we can change our bounds. So the lower bound of 0 would become 0 squared plus 1, or 1. The upper bound of 3 would become 3 squared plus 1, or 10. So we're going from 1 to 10, and now we never have to switch back to x's. So I have 1/2 times the definite integral from 1 to 10, 1 over u du. I have 1/2 times the natural log of the absolute value of u, evaluated from 1 to 10. Second fundamental theorem of calculus, 1/2 times the natural log of 10 minus 1/2 times the natural log of 1. Well, the natural log of 1 is 0. So we have 1/2 times the natural log. I can keep those absolute values, but I don't really need them, of 10. And we can get the approximate value of this, 0.5 times ln of 10. It's about 1.15 5, 1, or you could leave 1/2 natural log of 10. All right, several of these for us to do. Our first example, all right, well, doesn't look like it divides nicely. When in doubt, set that denominator equal to u. So then du is 3x squared plus 1. And look at that. The denominator is u. That numerator is our du. Sorry. Don't forget that dx on there. So we have the antiderivative of 1 over u du, which is natural log of the absolute value of u plus c. And replace u again with x cubed plus x plus c. Don't forget those absolute value symbols. They are not correct without it. All right, this one, we happen to know that the derivative of tangent is secant squared. So if u is tangent of x, du is secant squared x dx. We can substitute this all out. It is 1 over u du. And look at that, we get the natural log of the absolute value of u plus c. We have the natural log of the absolute value of tangent of x plus c. Remember that to check these, all we have to do is take the derivative, which we've been doing for months. All right, part C. This one looks a bit trickier, but I see a fraction that I can't really get rid of, so I'm going to use u substitution. U will be my denominator, x squared plus 2x, which means du is 2x plus 2 dx. Problem here is that we have x plus 1, not 2x plus 2. I can divide that whole thing by 2 though. I get 1/2 du equals x plus 1 dx. So all I have to do is put an extra 1/2. I have 1 over u du, which is 1/2 times the natural log of the absolute value of u plus c. So our answer is 1/2 times the natural log, the absolute value of x squared plus 2x plus c. And 1 over 3x plus 2 dx. Our u value will be our denominator, 3x plus 2, which means du is 3 dx. Well, we don't see a 3, so we divide it over. 1/3 du is dx. Plug those in, we have 1/3 antiderivative of 1 over u du. And look at that, 1/3 times the natural log of the absolute value of u plus c. Substitute that back in. 1/3 times the natural log, the absolute value of 3x plus 2 plus c. There we have it. All right, now we're going to get a little crazier. Well, the numerator is definitely not any version of the derivative of the denominator, but fractions are nice because we're going to work with it a little. I can actually break this apart. I could break it into as many pieces as I want, but this way, putting the x squared and the 1 together, putting the x separate, works out nicely. Notice that they both have the same denominator, but this first fraction becomes 1. Now, I just rewrote my integral as 1 plus x over x squared plus 1 dx. I can split these apart. Antiderivative of 1 dx plus the antiderivative of x over x squared plus 1 dx. I know the antiderivative of 1 dx. It is x plus c. Awesome. The second part, not quite so great. We need to use some substitution. So if u is the denominator, x squared plus 1, du is 2x dx. Divide that 2 over because we don't have it. 1/2 du is x dx. So this is actually 1/2 times the antiderivative of 1 over u du. And we can handle that. That's 1/2 times the natural log of the absolute value of u plus c. Don't forget this x plus c we have out front here. And and replace u. So we have 1/2 natural log of the absolute value of x squared plus 1 plus c. We also have our x plus c in here, but two different c's added together. We don't have to write them twice. We have x plus 1/2 the natural log, the absolute value of x squared plus 1 plus c for our final answer. All right, our next example. We're going to start by trying to find some u substitution. Ooh, but wait, is that going to work? Well, if u is x plus 1, then du is dx. We could use our method where we solve for x over here. So u minus 1 is x. So we could change this into 2 times u minus 1 over u squared du. And that is actually helpful. If I distribute my 2, I get 2u minus 2 over u squared du. And now I can break this into two separate fractions. I'll make it 2u over u squared minus 2 over u squared du. So really I'm finding the antiderivative of 2 over u minus, I'm going to call that 2u to the negative second power du. Well, the antiderivative of 2 over u is 2 times the natural log of the absolute value of u minus 2 times u to the negative first power divided by negative 1 plus c. Well, a negative, negative, we have 2 natural log of the absolute value of u plus 2 over u plus c. And then we will resubstitute the u. 2 natural log of the absolute value of x plus 1 plus 2 over x plus 1 plus c is our antiderivative. So some guidelines here. Learn those basic integration formulas. You now have 12 formulas, power rule, log rule, 10 trig rules, and by the end of 5-7, you'll have even up to 20. We'll find an integration formula that resembles all or part of it, and by trial and error, find a choice of u that will make the integrand conform to the formula. The more problems you do, the easier it will be to find what u should be. And if you can't find a u substitution that works, try altering it. You could try trig identity, multiply, divide, add, subtract, long divide, all sorts of things you can do to get it to something you can work with. And if you have access to a computer software that will find your antiderivative, you could use that to check. So let's look at this one. To solve a differential equation, this basically means get dy by itself. So we multiply the dx over. If dy is 1 over x ln of x dx, then y is the antiderivative of 1 over x natural log of x dx. We need a u substitution now. Well, I know the derivative of natural log is 1 over x. So if u is the natural log of x, du is 1 over x dx. And if I split this apart a little bit, I could call it 1 over x times 1 over natural log of x dx. So when I substitute, I actually have 1 over u du. And 1 over u du, I can handle that. That's natural log of the absolute value of u plus c. And u is the natural log of x plus c. And there we have it. The antiderivative of tangent of x dx. We do not have a trig rule that uses this one, but I do know that tangent is sine of x over cosine of x. Now when using u substitution in this case, you probably want to set u equal to your denominator, so our u would be cosine of x. Du then is negative sine of x dx. There we go. So that means I have an extra negative hanging out, so negative antiderivative 1 over u du. And look at us go. We have negative natural log of the absolute value of u plus c, and substitute back in the cosine of x plus c. And there we are. Next up, antiderivative of secant of x. Well, that's not one of our basic derivative rules, so let's try to think rationally about this one. This is one of those cases where we want to multiply and divide by the same value. And this gets wonky. So we're going to take the secant of x, we're going to multiply by something over itself, dx. And the trick on this one is to kind of guess and hope until we get something. But secant and tangent are related. So we're going to use secant plus tangent. Because then we get the antiderivative of secant squared plus secant tangent over secant of x plus tangent of x. Now our u substitution would actually be helpful. So if u is secant of x plus tangent of x, du is secant tangent, because the derivative of secant is secant tangent, plus the derivative of tangent is secant squared. Oops, you can't see that. There we go. Dx. And look at that. That matches our numerator. So we have the antiderivative of 1 over u du, which is the natural log of the absolute value of u plus c, and just substitute u back in. The natural log of the absolute value of secant of x plus tangent of x plus c. The tricky part here is figuring out that you need to multiply by secant of x plus tangent of x over itself. But there are 6 basic integrals of our trig functions. The antiderivatives of sine, negative cosine plus c. The antiderivative of cosine is sine plus c. The antiderivative of tangent of u is negative natural log of the absolute value of cosine of u plus c. The antiderivative of cotangent of u is natural log of the absolute value of sine of u plus c. Secant, we just saw that one. Cosecant is very similar, except that there's a negative out front, and with cosecant and cotangent. All right, let's try this out. So we have the definite integral from 0 to pi over 4 of the square root of 1 plus tangent squared of x dx. All right, well, 1 plus tangent squared, that's a trig identity. We are going 1 over 0 to pi over 4 of the square root of secant squared of x dx. And guess what? A square root and a square cancel each other out. 0 to pi over 4 of secant of x dx. We just figured out the antiderivative of secant. It's natural log of secant of x plus tangent of x from 0 to pi over 4. So now we plug in our 2 answers. Natural log of secant of pi over 4, my goodness, plus tangent of pi over 4, minus natural log of secant of 0 plus tangent of 0. All right, secant of pi over 4 is the square root of 2. Tangent of pi over 4 is 1. Natural log of secant of 0 is 1. Tangent of 0 is 0. Well, the natural log of 0, or 1, is 0. So we have just the natural log of the absolute value, square root of 2, plus 1. I could type that in a calculator. Meh, I'll leave it. All right, we have an average value. So remember, to find the average value, we take 1 over b minus a, so 1 over pi over 4 minus 0, times the definite integral from 0 to pi over 4 of our function, which is tangent of x dx. All right, well, 1 over pi over 4 minus 0, that's 4 over pi. The antiderivative of tangent of x is negative natural log the absolute value of cosine of x from 0 to pi over 4. So we have 4 over pi times the negative natural log of the absolute value cosine of pi over 4 minus negative natural log of the cosine of 0. All right, cosine of pi over 4 is square root 2 over 2. So we have negative natural log of square root 2 over 2 plus natural log of cosine of 0 is 1. Natural log of 1 is 0. So we have negative 4 over pi times the natural log of square root 2 over 2. Unless we want to plug that in a calculator, we can leave it. So now you'll have some assignment to practice this.